Project 3.4.1 SAR ADC Overview and Clock. So this is my breadboard of the clock, which is an astable multivibrator using NAND gates. So here is the NAND gate chip. These are 0.1 microfarad capacitors, and these are 510 ohms resistors. And right now it's showing a frequency of 10.08 kilohertz. However, I couldn't really find an equation online for calculating the frequency for this exact circuit, so I decided to do a little experimenting. So I tested with a few different resistor values and see what the frequencies would be. So these resistors are 1 kilo ohms, and the frequency appears to be 5.8 kilohertz. When I'm using 2.2K resistors, it's showing a steady 2.92 kilohertz. And for a 5.1K resistor, the frequency is 1.35 kilohertz. And when I use a 10K ohms resistor, it's fluctuating around 800 hertz. And I also tried to test a few capacitor values with the 510 ohms resistor. So here's the 103 capacitor, which is 0.01 microfarads, and it's giving about 97.8 kilohertz. So here is the data that I gathered. So for the 5 resistance values, I plot them out using an exponential graph, and the R-squared came out really high, so this is probably what it is about. So this is the equation for resistance versus frequency. And as for capacitance, I only had 2 bipolar capacitors, so I couldn't get that much data, but I just assumed that will also be a exponential function like the resistance versus frequency. So this is the capacitance versus frequency equation that I got. Combining those two, I got this formula to calculate the frequency in hertz using resistance in ohms and capacitance in microfarads. And if I try to calculate for the frequency using the 510 resistor and the 0.1 microfarads capacitor, which is what actually is in the circuit, this is the value that I get, 10,140, which is pretty close to the 10,080 hertz that I get from the actual circuit. So this is my Fossil diagram of the clock. So as you can see, as these capacitors charge and discharge, they change the input of the inverters, and therefore changing their outputs, and which charges and discharges the capacitors. And this causes the capacitors voltage to form like a nearly triangle pattern, and this creates an oscillation, and that's how it's an astable multivibrator. So I'm using 10 microfarads right here as an example to show the graph right here, but if I use 0.1 microfarads it actually uses in the circuit, it doesn't show very well. So this is the circuit diagram for the entire SAR ADC, where this is where the analog input comes in. It is being fed a analog voltage, and it's trying to convert it into 8 bits of digital voltage right here. So for the analog input, it goes through a LF39A sample and hold chip, and it puts it in this capacitor right here and holds it for the time that it takes the rest of the circuit to come up with the digital 8-bit value. And then after it's done, it releases it and takes in a new analog value and does the entire thing again. And basically how the circuit gets the digital 8-bit digital value is, first of all, this clock right here is giving the clock signal to this octa D flip-flop, so it basically controls the clock of the entire circuit. And what the circuit does is that, so basically it takes a 8-bit voltage created from this R2R ladder right here that I built in a previous project, and it changes the highest bit to a 1. And then using this comparator right here, it compares the voltage from the circuit to the analog voltage that's being provided, and gives out a signal whether it's larger than or is smaller than the analog's voltage. And if it's larger than the analog voltage, the bit will be set to a 0, and if it's smaller, the bit will be set to a 1, and that bit will be set right here in the output, and then it will move on to the next highest bit and does this whole comparison again. So basically it goes through all 8 of the bits and compares them each time to the analog voltage, seeing if it's larger or smaller than it. And this is where the SAR ADC gets its name from, the successive approximation register. It successively goes through 8 bits in a row, and it compares each of them to the analog voltage, therefore approximating a digital voltage to an analog one, and it stores it in an 8-bit register, hence successive approximation register. And this is the register for the 8-bit output. So basically for each of the bits that are being set, this is where it is set and being kept, and there's an LED on the output to show that if it's on or not. And this part is the switch, which switches it from manual to auto mode, so you can either control it in a manual pattern and step through each of the steps, or you can turn it on auto and let it do its thing, basically. And as for the central mess right here with all the flip-flops, the AND gates, and the resistors, so basically when a bit is being set to be a voltage to compare with the analog input voltage, so this bit is set, and this AND gate and the D flip-flops right here will decide if the bit should be on or not. The R2R DAC ladder will do its thing and give out an analog voltage from the 8 digital bits that's being given to it, and this analog voltage is being compared to the analog input voltage right here using this LM393 comparator, and if it is higher or lower, it will send a signal back to all these D flip-flops right here and determine if it should be higher or lower, and then store in the register.